Section 8 of Chapter 4 Equation of State is about shock compression. Shock compression is an experiment to make a body under extremely high pressure using shock wave. Then what is a shock wave? Shock wave is a type of propagating disturbance that moves faster than the local speed of sound in the medium. Typical example of a shock wave is associated with the passage of the ultrasonic aircraft or ultrasonic missile. This is some picture about a shock wave associated with the passage of the ultrasonic aircraft. At the top of the aircraft or top of the wing of the aircraft, because the velocity of the movement of these part is faster than the speed of the sound of the air, it produces a shock wave like this. So the shock wave is characterized by an abrupt, nearly discontinuous change in pressure, temperature, and density of the medium. This diagram shows the pressure change with the shock wave. Before shock wave comes, its pressure is standard pressure, and by the arrival of shock wave, the pressure suddenly increases, and this high pressure is kept a very short time, and it decays by expansion wave. As I told you, shock compression is an experiment to compress a solid or liquid by using shock wave. The simplest way is utilizing gas explosion. However, the shock experiment using gas gun is more popular. In this method, a high-velocity flyer is accelerated using a gas gun, and the flyer collides to the sample to produce a shock wave. More recently, laser ablation technique became practical. In this method, the instantaneous laser heating is made to the ablator, and as a result, the ablator suddenly evaporates, and this evaporation produces a shock wave. Let me briefly talk about the pressure, temperature, and time conditions of shock compression. This plot shows the pressure conditions of various high pressure experiments, and the most important merit of the shock compression experiment is its pressure range is extremely high. These are red circles represent the pressure conditions of generated by diamond anvil cell as a function of years of the study. So recently, the world record of the static diamond experiment reaches about 1 terapascal, but mostly the pressure range of diamond anvil cell is 200 GPa. On the other hand, shock compression using gas gun, which is expressed by this one, is reasonably rich 1 terapascal. In contrast, the recently developed laser ablation shock compression experiment can reach much higher pressure, and 10 terapascal is a reasonable target, and as shown in this diagram, it exceeds 10 terapascal recently. Temperature range can be high, but it is according to the pressure and material properties. In the terapascal range experiment, it can reach 10,000 Kelvin or more. Why temperature is increased is a large proportion of shock energy is used to increase the temperature in addition to the pressure. The demerit of shock experiment is duration is very short. It depends on the pressure and the size of the sample. In the conventional gas gun experiment, the range of the high pressure is about few microseconds, but in the recent laser ablation experiment, its range is nanosecond or something like this. This slide summarizes the advantages and disadvantages of shock experiment. Advantages are as follows. First, as I told you, the pressure generated by shock experiment is extremely high. The second, we can evaluate pressure without any secondary pressure scale, as I explained later. And we can evaluate density change, as explained later. Disadvantage is duration. Time duration is very short, from microsecond to nanosecond. And the temperature cannot be controlled independently from the pressure because temperature increases spontaneously due to the results of shock compression. And that temperature is difficult to evaluate. The temperature estimation contains large errors. In this lecture, I typically explain the gas gun type shock compression experiment. This method is conventional and therefore easy to understand. In this type of experiment, we have two quantities to measure. One is velocity of the flyer or projectile, which is referred to as particle velocity. It is regarded as the velocity of the motion of atoms or particles composing the material. The second one is shock velocity. This figure explains how to measure the shock velocity. This is sample part, and this is colliding projectile. This is other part, but anyway, the projectile collide from upper direction, and we put some markers which can be easily observed optically, and we take a photo of these markers with time. So this is photos of such markers, and horizontal axis is time, and vertical axis is the position of the markers with a different height of the sample. Then, when shock wave propagate, the markers start to move, and because of the difference of reaching the shock wave, the starting time of the moving of the markers are different as a function of the height. So from this height and the time relations, we obtain shock velocity. Let me show one example of shock compression data. This diagram shows the shock compression data of gold. Horizontal axis is particle velocity, and vertical axis is shock velocity. So shock velocity increases as a function of particle velocity, as we can imagine, and the shock velocity is expressed by quadratic functions in this study. So shock velocity is equal to 2.995 plus 1.653 over particle velocity minus 0.013 of times particle velocity cube squared. So in many shock experiments, we obtain these relations to obtain the equation of the state of the materials and the density and so on. Before talking about the theory of shock compression, let me talk about Fugonian elastic limit. Solids have a significant resistance to the shear. So, as a result, the solid resists the shock wave up to some conditions. Fugonian elastic limit is the conditions above which the matter behaves as a liquid. So this is example of alumina Al2O3. Horizontal axis is density and vertical axis is pressure obtained from the particle and shock velocities. This curve corresponds to the isothermal compression, and these points are shock wave data. So you can see there is a bending of the shock wave data as a function of density. So this bending is Fugonian elastic limit, and here density does not increase so rapidly, but pressure increase because of the resistance of the solid. In order to construct the equation of state, which we do not consider the resistance of the sample to the shear, the data above Fugonian elastic limit have to be used, and the data below the Fugonian elastic limit should be discarded. The example of in the case of Al2O3, as shown here, the Fugonian elastic limit is about 20 GPa because alumina is very hard. In the case of gold, almost none because it is soft. Let us have a more concrete image about shock wave using analogies. Shock wave is a ubiquitous result of matters moving at velocities faster than the speed at which adjacent material can move. So the first example is flow of the snow in front of a moving snow plow. So this is a snow plow, and snow plow pushing snow. Then this edge of the plow moves from here to this line during time for delta t. During this period, the front of the packed snow moves even faster and reaches here. At the zero time, there is no packed snow, therefore the position of the edge and snow front are the same. But after moving delta t, the fresh packed snow's front goes faster than the edge. So this is one example. This snow plow is particle or flyer, and the packed snow's front is shockwave front. Another example is moving train. So let us consider there is a very strong bull, and the train with box cars collide with the bull, and the bull is so strong he is sitting and does not move. Then the train still moves from left to right, but the front of the crushed box cars moving much faster from left to right. So this moving discontinuity separates undisturbed boxcars from crushed ones is shock wave. Here, let us clarify the terms of particle velocity and shock velocity. The particle velocity is the velocity that a given element in the body acquires as a result of shock wave passing over the element. And shock velocity is the velocity with which the disturbance moves through the body. So let us consider some example. For example, debris such as dust or paper blown by a gust of wind. So shock velocity corresponds to the wind velocity, and particle velocity corresponds to the velocity of debris movement. And as you can see, the wind velocity is faster than debris velocity. So shock velocity is always faster than particle velocity. From here, let us derive an equation for shock wave. The fundamental points to derive the equation of shock wave is the conservation of mass, momentum, and energy across the shock discontinuity. So we have three conservation equations, and from these three conservation equations we derive so-called Rankine-Hugoniot equation, which is E minus E0. E is and E0 are after and energy of the matter after and before the shock discontinuity, equal 1 over 2 times V0 minus V times P plus P0. V0 and V are the volume of the matter before and after shock discontinuity, and P and P0 are pressure after and before the shock discontinuity. Thus, this equation shows the relations among energy increase, volume change, and shock pressure upon shock compression. So we will derive this equation from the next slide. First, let us consider the conservation of the mass. So at time 0, the plow begins moving at velocity small u from its starting point. And at that later time t0 plus delta t, the plow has moved distance u times delta t. the discontinuity between loose and packed snow has moved at distance distance u times delta t. U is the velocity of the front of the packed snow. Obviously, large U is larger than small u. So the discontinuity has advanced ahead of the plow. It's clear, right? Then let us consider the mass of the unpacked and packed snow. So the mass snow in front of the blade was compressed. So before compression, the mass of the fresh snow to be packed by the plow is L, the length of the blade, times rho 0, the density of fresh snow, and U, velocity of the front of the packed snow, and time delta t. So in this case, rho 0 is not strictly speaking not density but the mass per unit area. But anyway, it is the area density. Then the mass of the snow between blade and the discontinuity here and here after time delta t is L times the length of the blade times rho 1. Rho 1 is the density of the packed snow, and distance between front of the packed snow and front of the blade. The front of the packed snow is, as we have already seen, large U times delta t, and the front of the blade is small u times delta t. Therefore, this length is large u times delta t minus small u times delta t. This one. As a result, the mass of snow between the blade and discontinuity is L times the density rho 1 times the velocity large u minus small u times delta t. Then these two should be equal. Therefore, we can cancel delta t as a result, and also cancel L, the length of the blade. We have rho 0, density before packing, times the velocity of the shock front u is equal to rho 1, the density after compression, times large u, the velocity of the shock front, minus small u, the velocity of the blade. This is a conservation mass. Equation 4.8.3. Next, let us consider the conservation of the momentum. To consider the conservation of momentum, let us consider piston fluid system instead of plow snow system. So this illustration shows the shock wave in the piston fluid system. So this blue circle indicates the piston, and the fluid is stored in the cylinder, and this blue piston well, this yellow plate moves in the velocity of small u, and this red circle shows the shock front. In front of the shock front, it's a state unshocked state, and this is the pressure is P0, density is rho 0, and energy is internal energy is E0. Behind the shock wave, the material was compressed, so the pressure is higher, P1, density is higher, rho 1, and internal energy is also higher, E1. During a time delta t, this blue piston moves by small u times delta t, and shock front has moved large u times delta t. The particle velocity is identical to the velocity of the piston. The particle velocity is the velocity of a particle of fluid caught up in the flow, and the shocked material carried with the particle velocity. So this is identical to the piston velocity. Then let us consider the conservation of momentum. Here we consider the pressures before and after shock wave. So pressure is P1 pressure is P0 before shock wave comes, unshocked part, and the P1 is pressure after shock wave passed through. Then net force on the system P1 minus P0 is applied per unit area. So this is equal to the increase in momentum per unit time. Then let us consider the increase in momentum for time duration delta t. The length of a shock wave passing over is u times delta t. U is a shock velocity. And the volume of the shock passing over is this length times area S. So U delta T S. Then mass of this volume is the density rho 0 times U delta T S. Then increased momentum is the rho 0 times U times delta T times S times the particle velocity U. Then conservation momentum is in the P1 minus P0 times S delta T, as we have seen in the last slide, equal rho 0 times U times delta T times S times U. As a result, P1 minus P0 is equal to rho 0 times U, large U, shock velocity times small u, the particle velocity. Equation 4.8.4. The last is conservation of energy. First, let us consider the work done by the piston. So piston pushes this liquid with pressure P, and the distance of movement is u times delta t. Forces are P1, pressure over this plane, times S, area S. Then the work is F times x, which is equal to P1 SU delta t. This work should be balanced by the kinetic energy acquired by the volume where shock wave has passed, which is 1 over 2 times m times u squared. M is the mass of the material accelerated by the shock wave, this region, which is equal to rho 0 times large u shock velocity times delta t. So then 1 over m times u squared is equal to 1 over 2 times rho 0 times u times delta t times u squared, then which is equal to rho 0 u large u small u squared delta t over 2. Equation 4.8.5. The work done by the piston is also used to increase the internal energy in the volume of the shock wave passing over, in addition to the kinetic energy. And the internal energy increase is given by this formula. E1 and E0 are internal energy of this material per mass before and after shock wave, and therefore E1 minus E0 is the increase of internal energy before and after the shock wave passing over, and U, the large U S delta T is the volume of the shock wave passing over, and rho 0 is density. Therefore, we equate the work done by the piston is equal to increase in kinetic energy and increase in internal energy. Equation 4.8.6. Then let us obtain the Rankine-Gonio equation, which is the energy change with respect to pressure and specific volume V, which is inverse of density, from the initial state to the final state by eliminating the shock velocity u and the particle velocity small u from equation 4.8.3, the conservation of mass, 4.8.4, conservation momentum, and 4.8.6, conservation of energy. First, let us start from the equation 4.8.3, which is rho 0 times the shock velocity u is equal to rho 1 density after the shock times the shock velocity minus particle velocity. So from this equation we have the shock velocity u is equal to the volume before shock wave arrives divided by volume before shock wave arrives minus volume after shock wave arrives times u, the particle velocity, 4.8.7. The meaning of this equation is clear from the analogy of the snow plow. If the volume becomes zero after a shock wave passing over, namely volume 1 equals 0, then there are no packed snow in front of the plow. Therefore, front of the shock wave is equal to is the same position with the plow. As a result, the shock velocity and particle velocity become the same, equal. So, if, on the other hand, if the volume does not increase by shock wave passing over u1 equal v1 is equal to v0, the u become infinite. So this phenomenon is understood from this figure. If the packed snow has the same density with the fresh snow, there is no front here. Instead, the front of the packed snow is infinitely far from the this snow plow, or just to the end of the fresh snow, because fresh snow and packed snow are identical. As a result, we can consider the shock front propagates infinitely fast velocity. Next, the equation of the conservation of the momentum 4.8.4 P1 minus P0 equal rho 0 large U shock velocity small u particle velocity by the equation conservation method. Equation 4.8.7 large U shock velocity is equal to V0 volume before shock divided by the difference of the volume before and after shock times the particle velocity u. Then P1 minus P0 is pressure difference before and after shock is equal to rho 0, the volume before shock, times V0 over V0 minus V1 u times u. And the rho 0 and V0 relations of the reciprocal relations. Therefore, this formula becomes u squared over V0 over V1. As a result, the particle velocity squared, u squared is equal to P1 minus P0 times V0 minus V1. Next, the equation of conservation of energy 4.8.6 P1u is equal to 1 over rho times the shock velocity u times the particle velocity u squared plus rho 0 times shock velocity large u times the internal energy difference E1 minus E0 times the shock velocity u times the particle velocity small u by the conservation equation of the conservation method 4.8.7 u equal V0 over V0 minus V1 u. Then P1 u is equal to 1 over to rho 0 V0 u over V0 over V1 u squared plus rho 0 times V0 u over V0 over V1 E1 minus E0. And again, the rho 0 and V0 are reciprocal relations with each other. They cancel here, here, and all terms have a u, factor u, then they cancel. As a result, P1 times V0 minus V1 is equal to 1 over 2 u squared plus E1 minus E0. Equation 4.8.9. We substitute the equation 4.8.9 P1 times V0 minus V1 minus equal 1 over 2 u squared plus E1 minus E0 by equation 4.8.8 u squared equal P1 minus P0 times V0 over V1. Then we have P1 V0 minus V1 is equal 1 over 2 P1 minus P0 V0 over V1 plus E1 minus E0. Then we simplify this equation. Then we have E1 minus E0. The increase of the internal energy is equal to 1 1 over 2 times V0 over V1 times P1 plus P0, equation 4.8.2. So this is Rankine-Hugoniot equation. This is referred to as jump condition. The difference of the internal energy between the initial and final state through the shock transition. The observed values are the shock velocity u, large U, and the particle velocity small u. We know the density or volume before compression and pressure before compression, and we can assume internal energy before compression. Therefore, let us express the volume after shock compression V1 using V0 and U, large U and small u. So from the equation of the conservation of the mass 4.8.3, we have V1 is equal to V0 times large U shock velocity minus particle velocity small u divided by shock velocity large U. So we can relatively easily obtain the volume of sample after compression. And from the conservation of momentum, equation 4.8.4, P1 minus P0 equal rho 0 times large U, the shock velocity U and particle velocity small u, we can easily express the pressure after shock compression, which is the pressure before compression P0 time plus the shock velocity u times the particle velocity small u divided by the volume V0, equation 4.8.4 prime. And from the Rankine-Hugoniot equation, we know the increment of the internal energy as a function of the volume before and after compression and pressure before and after compression. Then the pressure and the internal energy after compression E1 is equal to the energy before compression E0 plus the volume V0 times 1 minus shock velocity large U minus the particle velocity small u divided by the shock velocity large U times the pressure before compression plus 1 over 2 times the shock velocity U times large U times the particle velocity small u divided by volume V0 before compression, equation 4.8.2 prime. Estimation of the temperature at the shock compression is very tricky. The energy increase is easily obtained E1 minus E0 by the Rankine-Hugoniot equation. Then we can separate the internal energy increase into two parts. One is internal energy increase by compression from V0 to V1 at temperature T0 before compression, and delta E Th is internal energy increase by heating temperature increase from T0 to T1 at compressed volume V1. So the delta ETH is equal to the heat capacity at constant volume from temperature T0 to T1 at volume V1. And we approximate the heat capacity CV by Debye model like this. So theta D is divide temperature at V1. And the divide temperature after compression at compression V1 can be expressed by the divide temperature at volume before compression V0 times exponential function of Grunizer parameter divided by the compression volume exponent of Grunizer parameter times 1 minus V1 over V0 to power q. Then the first time delta E T0 from the first and second law of thermodynamics equation 1.1.5, the internal energy increase is temperature times entropy increase minus pressure times volume increase. Then the internal energy increase by compression from V0 to V1 is expressed in this way. So T0 times ds, the integral with respect to entropy S, minus pressure at temperature T0 with respect to volume. Then T0 is the first part is T0 times entropy at temperature T0 and volume V1 minus entropy at temperature T0 and volume V0. Second term is integral over pressure T0 at temperature at temperature T0 with respect to volume from V1 to V0 to V1. And entropy difference is entropy at T0 and volume V1 is integral of Cv at volume V1 divided by over T with respect to temperature from 0 to T0. And the entropy of T0 V0 is same. So we inversely calculate these equations and we obtain T1 by this inverse calculation. So we have three equations, equation 4.8.2, 4.8.3 and 4.8.6, namely the equations of conservation of mass, conservation of momentum, conservation of energy, and one static equation of state for 5 variables: pressure, volume, energy, shock velocity, and particle velocity. Therefore, there is only one independent variable. So we have one curve in PV, EU, large U, small u space. This curve is referred to as Rankine-Hugoniot curve or simply Hugoniot. It can be represented in any two-dimensional plane, PV or P as particle velocity U or shock velocity large U, particle velocity small u. This is one example, pressure against volume. So these open symbol represent the shock experiment data, and this red curve is Hugoniot. Please note that Hugoniot is not a curve of locus of sample follows in one experiment. It is a accumulation of data at different experimental conditions with a different particle velocity. So, yes, let me argue the Rayleigh line. Rayleigh line is a line connecting the initial and final shocked state. From the equation 4.8.8, the particle velocity squared is equal to p1 minus p0 times v0 minus v1. With the equation 4.8.7, the shock velocity large U is equal to v0 over v0 minus v1 times the particle velocity U. So from the equation 4.8.8, we directly have the particle velocity U is equal to square root of p1 minus p0 times v0 minus v1. Then shock velocity U is equal to v0 over v0 minus v1 times the particle velocity U. Therefore, square root of p minus p0 divided by v0 over v. So the slope of the Rayleigh line is equal to the slope of Rayleigh line in the pressure and volume space is p minus p0 divided by v minus v0, which is equal to minus u times v0 squared from this equation. Therefore, with increasing shock velocity u, the slope becomes steeper rapidly. Therefore, Lugoniot is curved downward. Finally, let me argue kinetic and internal energy increases by shock compression. This figure is the same as the previous slide. The kinetic energy is from equation 4.8.8, 1 over 2 times the particle velocity squared, and which is equal to 1 over 2 times p minus p0 times v0 minus v. In this figure, this quantity is equal to the area of this red triangle. So this is this length is a v0 minus v, and this length, vertical length, is p minus p0, and we divide by 2. Therefore, it is the area over this triangle. On the other hand, internal energy increase can be obtained by the Rankine-Lugoniot equation 4.8.2, which is energy increase E minus E1 is equal to 1 over 2 times P plus P0 times V0 minus V. So V0 minus V is again this length, and the P plus P0 divided by 2 is this middle point over P and P0. Then this is equal to the area of this blue figure. And when the initial pressure is 0, P0 equals 0, so if this is 0, this area diminishes. Therefore, the blue area and red area, namely the kinetic energy and the internal energies, are equal, which is 1 over 2 P times V0 minus V. So this P0 diminishes, then it becomes like this one, and this P0 diminishes, then this becomes this one. So both the internal energy and kinetic energies are equal. So the internal energy increase is equal to the kinetic energy increase if the initial initial pressure is 0. So this is the end of the section 8, shock compression.